All right, so last class we talked about the definite integral, right? And how we can use the antiderivative to find the area, the net area between a function and the x-axis. And we have the fundamental theorem of calculus that allowed us to do this. And so if we can find the antiderivative, all we have to do is evaluate it at the two endpoints of the interval. And we said that this right here represented, like if you took a rectangle in here, it would represent the height of it would be the f of x, and then this part here would be the dx. So we're taking a bunch of rectangles and adding up an infinite number of them, right? That's the basic idea from last time. And your homework was really just to go back and look at some old problems that you've already done and just include that part, all right? So we have an exam a week from today. Please expect to see a review. I'll try and get that out today if I can for that exam. And then we're gonna start 6.6 improper integrals. This will be the last section of chapter 6, and then we're gonna move in chapter 7 next time. If we get to it, I don't know if we'll actually get out of chapter 6 this week. We'll see. But let's get going. Were there any questions before I get going here? Okay, so improper integrals. So what we've done up to this point, we only spent one day on it really, is looked at, we can find the area below a curve on some finite interval, right, from A to B. But what if we wanted to find the area under a curve? Maybe that function starts at A, and then maybe that function just continues, I don't know, maybe it has like a horizontal asymptote and it keeps going, gets closer and closer to the x-axis. And what if we want to know that area underneath this, but forever, like in that direction forever? Seems kind of odd, doesn't it? I mean, if there's area over here, right, as long as it doesn't touch the x-axis and it stays above the x-axis just a little bit, approaching it asymptotically, does it even make sense to you? Like in your mind, does it make sense that we would have an area that's finite? Or does it seem like it would always be infinite? Do you know what I mean? It's kind of a right? So first thing we're going to do is figure out what the notation looks like if we want to do this, all right? If we want to take this and we want to go forever, right? Out here to infinity. So what we do is we change the notation. We say, okay, we're going to go from A, right, the left endpoint. We're going to go to infinity instead of to B, right, instead of some finite number. And what are we doing? Well, we're adding up again all those rectangles, the area, height times width. And the question is, do we get an answer or not, right? Do we get a finite answer? But remember, over here in the fundamental theorem of calculus, we have to evaluate the antiderivative at B, right? And what would B be for us here? Infinity. So how do you evaluate something at infinity? Like you can't plug infinity in, right? Because it's an idea, right? It's not a number. So what we're going to do whenever we see this notation is we are going to do this, all right? We are going to say that this is equal to the limit, and we usually use the letter t, as t goes to infinity, of the integral from a to t of f of x dx. So what we're saying is, can we do what we did over here, right? Do what we did over here, but when it comes to the part of evaluating, we're going to do a limit, and we're going to let this number that used to be b, right, used to be a fixed number, we're going to figure out what happens when that goes to infinity. Does that make sense to you? All right, so let's do it. Let's do an example, all right? And for the first example, the function I want to use is the function 1 over x squared. So as your first example, let's find the integral. Let's go from 1 to infinity of 1 over x squared dx. Now I'll put this over here just so we have it. Integral from a to infinity, f of x dx equals the limit as t goes to infinity, the integral from a to t, f of x dx. Right, that's what we're going to be using, right? So might be useful if we know what this function looks like, right? What does 1 over x squared look like? So if we went to Desmos and graphed this, it would look like this. Oh, sorry, that's 1 over x, sorry. 1 over x squared looks like this. Okay, that's what it looks like. And what we're trying to do is figure out, does it even make sense to find the area from 1? Let's see, if I plug 1 into that, I get 1, right? So from here over forever, the question is, what is that area? And is it even finite, right? Does it even give you a finite number? I mean, doesn't it seem like that area is just going to continue to grow? Like you'll just continue to contribute area no matter how far you go out? But still, is it finite or not? We'll see. So we're going to go replace the infinity with a limit. We're going to let t go to infinity, and we're going to go integral from 1 to t of 1 over x squared dx. And now I'm just going to use my fundamental theorem of calculus. I'm going to see if I can find the antiderivative, right? So what is the antiderivative of 1 over x squared? So should be negative 1 over x. Now you could do that by rewriting this like that, and then using your power rule for antiderivatives, right? Add 1, then you have to put 1 over that on the outside. So we get that. Now I'm using again from last class, we wrote that evaluation bar, then I'm missing something here. Sorry, I forgot to put the limit. Sorry. Don't forget the limit. That would be a mistake. So we want negative 1 over x, right? Evaluation bar 1 to t, like that. So I have found the antiderivative of this here, put the evaluation bar from the last class, but at the end of the day I have to take a limit, all right? So now I'm going to rewrite the limit again. And now I'm going to just put a set of brackets here. What I need to do is I need to plug t into this, right? So I plug in t for x, and then I subtract from that what I get when I plug in 1. So all I'm doing there is this right here. Capital F of b, that's capital F of b, and then capital F of a. Capital F of b minus capital F of a. Any questions? No? All right, so now we're back in Cal 1. We have to evaluate a limit. We have to see what happens as t goes to infinity, right, on this expression. Well, here's t, right? What happens as t grows? Well, it shrinks, right? Negative 1 is fixed on top, right? Negative 1 is fixed, and the denominator gets huge. What happens when your numerator stays fixed and your denominator gets huge? The ratio goes to 0, right? So this, when I apply the limit, right, so no more limit because I'm letting this right here, right, go to infinity. This whole thing goes to 0. And if that goes to 0, then I have 0 right there. And then this is minus 1, right, which is just plus 1. So our answer is 1. Which means that area is finite. It's finite, which is a little bit strange, but we have to understand what this is actually telling us. It's saying that if we take that curve, right, that went like this, if we take that curve and we try and find this area, no matter where I stop, okay, let's say I stop here at 100, right, and find that area, that's going to give me a number, isn't it? I promise you that that number is smaller than 1. It's probably pretty close to 1, but it's smaller than 1, all right? And if I go out to, I don't know, 1,000, now it's going to be, the area will be definitely bigger than this was, right? But still, it's going to be less than 1. And the further out you go, the closer and closer and closer and closer you get to 1. So maybe the area here, was like 0.95. I don't know, I'm just making it up. And then maybe if you go out to here, maybe it's 0.99997. And then if you go out further, it's going to be maybe 0.9999999999992, right? Or something like that. No matter how far you go, you're never going to exceed 1. And if you could go to infinity, it is 1, which is odd, but it's the way it is, okay? Make sense or not? Okay? All right, ready for another example? Let's do the same problem. Let's change the function. Now let's do, I don't know, let's do 1 over x instead of 1 over x squared. Now, the graph of this, just so you know, the graph of 1 over x looks like this. We're going to go from 1 to infinity again. What do you think? Do you think we'll get a finite answer still? We're going to find out, right? Okay, limit t goes to infinity. Integral 1 to t of 1 over x dx, which equals, I do the limit again, t goes to infinity. Okay, what is the antiderivative of 1 over x? Natural log of the absolute value of x, right? Natural log of the absolute value of x. Now, I'm not going to put absolute value on x, and the reason I'm not going to put the absolute value is because I'm looking on the interval between 1 to infinity, right? 1 to t. These are always going to be positive numbers. So I don't need to worry about the absolute value. It wouldn't be wrong to have it, but I just don't need it because the interval I'm looking at is always positive. Make sense? Like the thing's being plugged in. Okay, so I still need the evaluation bar. I put 1 to t here, right? And now limit t goes to infinity. I'll do a bracket. Set of parentheses here, set of parentheses there. This is going to be my capital F of B minus capital F of A, fundamental theorem. All right, let's plug t in. I get natural log of t. Let's plug in 1. I get natural log of 1. And now I have to let t go to infinity, right? Let t go to infinity. Now, in the previous problem, we had here like negative 1 over x, right? And that went to 0. But this doesn't do that, right? Think about what the natural log function looks like. If you were to graph natural log, this is what natural log of x looks like. So what happens if I start plugging in values into the natural log that get bigger? What happens to this graph as you go out to the right? What does it do? It grows. It's slow, right? It's not real fast, but it does grow. And it keeps growing and growing and growing. So where's this thing headed? It's headed to infinity, okay? Minus natural log of 1 is 0. So you get infinity minus 0, right? Which means you get infinity. And what does this mean to us? It means that that area is becoming unboundedly large, right? It's becoming infinitely big, the area. Even though this asymptotically approaches 0, just like the other one did, it doesn't approach 0 fast enough. So the area just keeps adding up. So the analogy here is that if I go out to 100, here's what I can tell you. That area would be some number, okay? Whatever, some number, right? If I went out to 1,000, what can you tell me about that? It's going to be bigger than that number, right? It's going to be bigger. It's going to be some other number here. And how do I say this? This one right here is bigger than this, right? But if you give me a number, how do I say this? Isn't this what the other one did? The other one did this as well. It was like 0.992, and then this one was 0.99997. So this one was bigger than that, right? Just like in the previous. But there's something else. I can't say that it never gets bigger than 1. What I can do is, like, let's say that you challenge me and you say, no, this area is not infinite. This area will never be 1,000,000, right? The area under here will never be 1,000,000. I can go out I'd have to calculate, but I can go out to some place where that area will be bigger than 1 million. And then you say, okay, well, fine, 2 million. Well, I just go out further, all right? In the previous problem, no matter how far you go out, you never get past 1, right? Do y'all see the difference between those two ideas? Yes? Yes. So what do we say for our answer? Well, infinity is our answer, but when it comes to these types of integrals where we have an infinity here, at the end, if we get something here that's not a number, okay? This is not a number, right? Infinity is not a number. If we get something that's not a number, then we will say that this integral diverges, right? It's the first time we're going to use this word. So we're going to say this integral diverges. In the previous problem, when we got 1, our answer is 1, but we would say that that integral converges, all right? Now, this is in the notes. I'm saying it now, all right? So diverges. So let me show you in the notes what I'm going through here. So these integrals we're doing right now, there's 2 types of integrals in this section. This is the first type we're going to look at. These are called infinite intervals. Does that make sense? Infinite intervals. Look at our interval. We go from where? 1 to infinity, right? That's an infinite interval, right? When you have infinite intervals, your integrals will look like one of the following 3 types. So what I've just shown you here is the one on the far left. We were going from a to infinity, right? A to infinity. So from some number to the right forever. The second type, which I haven't shown you an example, would be we go from some number to the left forever, right? And the third one there is we go in both directions forever, all right? Those are the 3 types of infinite interval integrals. Infinite intervals. Now, this is the definition. This is just me basically stating the definition again, showing you a geometric example. This is the second type where we go out to the left forever. Again, that's going to be a limit. We're going to do examples. What I really want to get to is that right there. If these limits exist, because remember in Cal 1, limits either exist or they don't, right? And the limit can exist or it cannot exist. If the limit exists, so if we get a number at the end of this, then we will say it is convergent, right? Is a convergent integral or it converges. And if we get something other than a number, like infinity or maybe does not exist, then we will say it diverges or it's a divergent integral. Okay, let's do something else. Let's do one where we go out. How about where we go out to the left? How about we do that? Let's do this one. How about the integral from negative infinity to bless you. To let's say, where do I want to go to? 0 of 1 over 4 plus x squared dx. What do you say we take a look at that on Desmos first? Take a look at that graph. Man. All right, so I'm going to graph this 1 over 4 plus x squared, and I'm only going to look at it from, say x less than or equal to 0. That'll work. So there's the graph. Okay, and we are trying to find the area underneath that, right? Call this f of x equals that, and then let me graph. is that doing that? There we go, greater than 0. There. All right, so that's what we want, right? We want that area, we want the area to the left of 0 forever. Forever and ever and ever, right? And as we go down here, you can see, no matter how far we go, if we zoom in, right, we've got area, right? There is area in there. We want to just get the total of all of this area together. So the only thing I'm going to do different here than in the previous one is when I set up my limit, I'm going to be replacing this with t instead of the upper limit with t. And I'm also going to have to make sure that my t isn't going to go to positive infinity, it's going to go to negative infinity. And then here I replace this with t, leave that as 0, and then 1 over 4 plus x squared dx. Okay? Now, what do you need? You need the antiderivative, which is going to be formula 17. So hopefully you recognize that. This is going to be from formula 17 in your formula sheets. Limit t goes to negative infinity. Okay, the antiderivative of that, according to formula 17, would be 1 over a. So what's a for us here? 2. So 1 over 2 inverse tangent of x over 2, right? X over 2, like that. And then we're going from t on the bottom to 0 on the top. And then we just rewrite the limit. T is going to go to negative infinity. Okay, bracket, do 2 sets of parentheses here. Right, this is fundamental theorem of calculus, capital F of B minus capital F of A. So what are we plugging in first? The 0, right, goes in here first, right? 0 goes in there first. So 1/2 inverse tangent of 0 over 2, which is just 0. And then we have 1/2 inverse tangent of t over 2. Right, students always seem to have an issue with this, so let's talk about this because it's confusing the first time you see it. All right, this right here is just 0, right? And so this, I really just want to know what tangent inverse of 0 is, right? Tangent inverse of 0, I need to know that. And then over here, I need to know what tangent inverse of what? This is weird, right? We're going to take a limit. Where's that going? Negative infinity. What's negative infinity divided by 2? Still negative infinity. So this is, again, this is not a number, it's just an idea. What's the inverse tangent function doing as I go to negative infinity? Right? That's what we need to figure out. And then what is inverse tangent of 0? So how do we do that? How do we figure that out? Here's how I recommend you look at this. I recommend that you think about, I'll do it in red, that you think about what the graph of y equals tangent of x is, right? Y is tan x. So back in pre-cal, we learned that the tangent function, this is also in your formula sheets, but you should know it. This is what the tangent function looks like. And where do these vertical asymptotes occur? Here? What? Not for tangent. It's negative pi over 2 and pi over 2. And so we have these vertical asymptotes like this. And then over here we have the same thing. And then the tangent function repeats itself, right? Keeps doing that in both directions. So when you see this, what this really means, or what you should be thinking it means, is tangent, not inverse tangent, tangent of what angle gives you 0. So look at this graph. Here are your angles, right? Here are your angles. What angle do you need to plug in to get a y coordinate of 0? You need 0, right? You need to plug in 0. When you plug 0 into tangent, you get 0. So this should be equal to what? 0, okay? Now, this one is the one that's real tricky. You're saying here, let me put it up here. This is saying tangent of what angle gives you negative infinity. Well, you can't get negative infinity, can you? You can't, because how do you get negative? It's not, negative infinity is not a number. But remember, this is a limit, right? This is a limit. So what angle must you be approaching in order to get negative infinity to come out of this function? Negative pi over 2, right? As I go and I approach negative pi over 2, where's the tangent function headed? Down here to negative infinity, right? So what angle produces a negative infinity coming out? It's going to be negative pi over 2. Had this been positive infinity, had it been positive infinity, then what would it have been? Positive pi over 2, okay? So this right here means that that angle must be negative pi over 2, which means that this is negative pi over 2. When you take a limit, that's what it's approaching. Does that all make kind of sense to everyone? Yeah? No questions? We're not done, right? We need a final answer here. Let me put it here. So here's where we were, right?
Yeah, I have a question.
Oh, I didn't see it.
You plug arctan of 0 into your calculator. Is it going to spit out 0?
Arctan of 0 on your calculator will spit out 0. But most calculators can't handle this, because most calculators don't have an infinity key. Some do, but most don't. All right, so where are we? I'm on this line right here, right? This equals, I've already taken the limit. So this we said was 0, right? 0. Take away. And then this came out to be, don't forget the 1/2 in front, right? 1/2. And then what was this? Negative pi over 2. So what does that turn out to be? Positive pi over 4. Positive pi over 4. The area underneath that curve to the left of 0 is positive pi over 4. All right, who has questions? It's all right? All right, let's do another one. How about this? How about if I want to do the same problem, but from negative infinity to positive infinity? That would mean both sides, right? Well, we could just double our answer, couldn't we? Just based on the symmetry, do you think this function symmetric? I think it is. Let me see. Let me not restrict it. Let me show you when we have both sides. Okay, you'll see if we do both sides. You'll see we have symmetry here. So our answer should be what? Double this, right? Double this should just be pi over 2. But let's just start the problem from the beginning, all right? Let's act like we don't know that there's symmetry, and let's just do this. How would you do it, right? So this is the third case. Do y'all see? I've given you 2 cases so far. The first 2 examples, we went from a number to the right forever. And in this example, I went from a number to the left forever. Now we're going to go left and right forever. So how do we do it? Well, here's how it's done. Whenever you have an integral with an infinite interval from negative infinity to infinity, the first thing we do is we break this integral up into 2 integrals. Let me write it down first, and then I will explain. So what I did is I said, okay, if you want me to go from negative infinity to infinity, what I'm going to do is first figure out what happens when I go from negative infinity to 0. And then I'm going to add to that the integral from 0 to infinity. Now, why did I pick 0? Well, 0 was a number between negative infinity, infinity, right? The symmetry I don't even care about, okay? I don't know who said that. I could have picked any number I wanted to, all right? I could have gone from negative infinity to 2, and then 2 to infinity. But it just makes sense to just kind of go right in the middle, right? Again, I'm acting like I don't see that graph. I mean, that graph definitely, if I see that graph, I would probably just do this problem and double my answer because of the symmetry. But I'm not, next problem, or a problem we're gonna do here in a minute, doesn't have symmetry. So we gotta pick a point, something in between. 0 is a very natural place to pick in between. Now this problem, we've already done, right? We just did that one, and we got pi over 4. Plus, now this one, even though we can pretty much guess it's gonna be pi over 4, I'm gonna go through the work again, all right? So for this one, I'm gonna rewrite this as a limit. I'm gonna go t goes to positive infinity, integral 0 to t, 1 over 4 plus x squared dx. That's me just rewriting that integral using a limit instead of the infinity. And then let's just say this is equal to pi over 4 plus limit, t goes to infinity. Okay, formula 17 again, right? So 1/2 inverse tangent of x over 2 evaluated at the 2 endpoints. This time 0 is on the bottom, t is on the top because of this order here. Hey, just FYI for everybody, we just went to a new email system, like everybody. And so you know how we use Canvas for email? Nothing has changed there. You should be able to get in touch with me. But if for some reason you're trying to contact somebody outside of the Canvas using your alamo.edu or whatever it is, that one, yeah. Well, I'm just telling you, if you're emailing someone, like we just migrated to a different system, so just give it some time. If you're not hearing back from someone, that's what's going on. Yeah, yeah. So just wanted to let y'all know, because I came in this morning, I couldn't get to my email, but I got to it finally. It's a pain in the butt. All right, so now pi over 4 plus. Okay, now here, this is going to be a limit. T is going to go to infinity. We're going to have 2 pieces here, again. Fundamental theorem of calculus. And now we plug in first, what goes first? What gets plugged in first? T, right? T first, T over 2. And then 1/2 inverse tangent of 0 over 2. All right, this right here